Lecture 3, Circular Motion. This is into Chapter 6, Circular Motion and Other Applications of Newton's Laws. Not all the lectures in this course are going to take up about the same amount of time, so this one's going to be a little bit of a shorter one. A radial force is one that's directed perpendicular to the direction of motion. We've already looked at this. We've seen radial acceleration. Good to know v squared over r is radial acceleration, so radial force is just mv squared over r. A particle in non-uniform circular motion has both a centripetal acceleration and a non-zero tangential component of acceleration. Applying Newton's laws from a non-inertial reference frame. An observer in a non-inertial frame must introduce fictitious forces. So if you were going to be looking at it from the perspective of a rotating object, then you may have to introduce centrifugal force to describe what's going on. Resistive forces. A body moving through a liquid or gas experiences a resistive force that depends on the speed. The resistive force generally increases with speed. The magnitude of the resistive force depends on the shape of the body and the properties of the medium through which it's moving. We'll look in more detail about how we would get that when we get to advanced dynamic problems too. Now for a question for today. How to lose weight on your tropical vacation. Sounds good. Part 1. Assuming the Earth is a perfect sphere with radius 6,400 kilometers, find the fraction that your effective weight decreases by at the equator compared to the North Pole due to the Earth's rotation. So the Earth is rotating, and as a result of this, when you're at the equator, then you have a tendency, if the Earth was rotating fast enough, you would just fly off it despite the Earth's gravitational force. So on a scale, it's going to seem like you have a little bit lower of a weight if you're at the equator. We're going to need to know the radial acceleration required to move in that circular path of this radius, and then subtract this from g to find the new acceleration that the normal force has to oppose when you stand on a scale. All right, this is basically a units problem. The rotational period is 1 day, and you know there's 24 hours in a day and 3,600 seconds in an hour, so that's 86,000 seconds. Velocity is r 2 pi over the period, so omega, r omega, or 2 pi over period. Centripetal acceleration would be ar is v squared over r omega squared, r t pi over 2 pi over period. For the Earth, we get a radial acceleration of 0.0337 meters per second squared. And since we're going to take gravity as 9.8, so near the Earth's surface, this is a relative change of negative 0.34%. So relative change of negative 0.34%. I'll just put the negative sign in there. There we go, negative 0.34%. What does that mean? Well, it's not going to be very much weight difference just from the rotation of the Earth. But hold on a second. We forgot to consider the Earth's rotation around the sun, right? So at night, your solar centripetal acceleration should line up with your terrestrial centripetal acceleration for maximum weight loss. Find your solar centripetal acceleration. So some information. The sun is about 500 light seconds away, and the speed of light is about 300 million meters a second. So we'll just proceed like last question. And oh dear, it's even lower. So this is a relative change of only 0.06%. And there's some more bad news. The logic in part 2 is faulty. Can you think about why? I'll give you a hint. It doesn't have to do with the numbers involved. It has to do with the conclusions we might have decided about that our rotation around the sun, because of that, we can get a weight, an effective weight loss from our force on the Earth. Well, we're in free fall around the sun. We're orbiting the sun, as it's known. So we don't actually feel that acceleration. The centripetal acceleration around the sun is provided by the sun's gravitational force. We're constantly accelerating towards the sun in the radial direction just to be in this orbit. If we were to build a massless Dyson sphere, so this gigantic sphere in the solar system, a theoretical device capable of harnessing all of a star's energy, and if we built one with the Earth's orbital radius and then just stood on that so that we weren't rotating, then we'd feel the sun's gravitational force, which would seem to us like 0.06% of what we experience as g from this last calculation. Part 4, where we're going, we don't need roads. If you move fast enough that you're orbiting the Earth, then you can travel forward without losing altitude. So we can maybe orbit at the Earth's surface. How fast would this be? We're going to again assume the Earth is a sphere of 6,400 kilometers. And just for fun, express your answer in meters per second, kilometers an hour, Mach number, which is fractions of the speed of sound, that we'll take as 343 meters a second, and fractions of the speed of light, 300 megameters a second. Little side question here. How much faster is light than sound? Roughly 1,000,000 times. Light's roughly 1,000,000 times faster than sound in air. Okay. So this is basically saying how fast do we have to be going before g is equal to the radial acceleration we calculate for the Earth's surface. Well, v squared over r at the radius of the Earth, we can solve this equation for v and find that we need to be moving 7,900 meters a second. Let's figure out some conversions here. A meter per second multiplying by 1,000 meters per kilometer in the inverse, so 1 kilometer per 1,000 meters, and 3,600 seconds an hour gives us 3.6 kilometers per hour is a meter per second. That's also good to know. So if you're thinking, well, I'm gonna run at 10 meters a second. That sounds reasonable. Well, that's 36 kilometers an hour. That would be pretty fast. 1 meter per second in terms of Mach number, well, the speed of sound is 343 meters a second, so 1 meter a second is 1/343rd of a Mach, or 1/343rd of Mach 1. 1 meter per second is c divided by 300 million, right? So it's 1/300 millionth the speed of light. Multiplying these conversion factors by our meter per second here, we can say the velocity that you need to be writing is 7,900 meters a second, or 28,000 kilometers an hour, or Mach 23, or 2.6 e-5 c. So Mach 23 would be an insanely fast speed. This means that you would be orbiting the Earth at its surface. Is it possible to actually go this fast? So imagine you're in somewhere that's super flat, like Saskatchewan, or you're just at a very low altitude where you're still above the buildings and all that. Could you go this fast? Your biggest problem is probably going to be air resistance. So it's going to be quite difficult to cool down all of the frictional heating you're going to be getting. At time at writing, the land speed record for something with a person in it is about 1,200 kilometers an hour. The SR-71 Blackbird still holds the airspeed record for a person in it at 3,500 kilometers an hour. These are quite a lot lower than the 28,000 you'd need to be orbiting the Earth. Bullets travel at about 3,000 kilometers an hour, so that's kind of interesting. The Blackbird travels faster than a 50 caliber bullet. Still, unmanned vehicles are quite a lot faster. The fastest thing ever flown in the Earth's atmosphere was a Collode rocket at 6,900 kilometers an hour. Air friction, again, biggest limiter. Without that, we can go way faster. So NASA's Juno spacecraft slingshotting around Jupiter reached 150,000 kilometers an hour, and the Helios 2 probe reached 250,000 kilometers an hour. You can find a story on the internet about a testing of an atomic bomb that inadvertently was quite a lot more powerful than intended, and possibly blew a steel plate into a speed at the Earth's surface as fast as the Helios 2 probe. So at least for a little while, this manhole cover or steel plate was going at around 250,000 kilometers an hour. But it was going straight up and not sideways, what it would need to be going to orbit. It's possible that escaped. We don't have a lot of evidence about that. I'll let you see if you can find that story. So then, with all of this considered, what do you think the fastest man-made object is? Well, it's a photon. Speed 100% c.